Carpenter X. Hi everyone, welcome back to another CAE tutorial with Carpenter X. Today's study is about the tank series with feedback control. This study demonstrates a system of 3 CSTRs. The feedback loop continuously adjusts the concentration of the feed stream entering the first tank to ensure that the concentration of the product leaving the third and final tank remains constant at the desired level. We'll use the reaction engineering module to further our study. The same unimolecular liquid reaction takes place in aqueous solution in each unit. The feed inlet streams connect the reactors to each other. It is assumed that the reactor volumes are constant and that the reactant fluid has a constant density. Overall, the feedback control system works by continuously monitoring the error between the desired and actual concentrations, calculating a correction base on the error and its integral, and adjusting the inlet concentration accordingly. It is clear to us that the integral can be evaluated by solving an ordinary differential equation. The ordinary differential equation is specified by adding a global equation along with the global ordinary differential equation and partial differential equation interface to the model. So I'll demonstrate how to do this while conducting our study. Here are our global definitions parameters. I'll provide this in two formats, the text file format and the CSV file format. Also, I'll upload this via Google Drive so you can have access to it. Let's begin. So let's navigate to our model wizard. Let's go over to OD. Let's go down to chemical species transport. Let's expand that. Reaction engineering, add. Let's click on study. Under general studies, let's click time dependent and select done. Let's head over to our global definitions parameters, and we're going to upload our text file or CSV file. So we can select this, we can click load, or we can just select right here, and you will navigate to your folder. I'm already in my folder where I have the text file located, and if I change it to CSV file, I have my CSV file here as well, but I'll use the text file. So I'll select that, open, and here are all of our global definitions parameters. You can expand them out to see them clearly. Okay. Let's navigate to our model builder, and under component 1, let's select reaction engineering. Let's change the name to tank 1. The interface name will help you to keep track of the variables that belong to the physics interface. In this case, the reaction engineering interface corresponds to a tank reactor, and to keep this in mind, the interface name was changed to tank 1, so that's why we changed it to tank 1. Now let's stay in our settings for reaction engineering. For the reactor type, let's change that to CSTR constant volume. Let's go down to our mixture properties and let's change the phase to liquid. Let's go back up and look for our mass balance, the volumetric rate, automatic, and let's change this to VR underscore tank. If we navigate back to our parameters, this is actually the first parameter. So that's the importance of setting up our parameters so we can just input them where we need them. Let's now navigate to our reaction engineering toolbar, and we are going to select reaction, and for the formula let's enter A equal greater than B right here, and let's click apply. For the rate constants, let's enter that, and also that should be in the global definition parameters. So if we go back to that, we'll see it here. Let's navigate back to our model builder, and we're going to set up our species. So let's start with A, and under our molar mass, let's enter uppercase M, lowercase n, underscore uppercase A, and for the density, let's enter lowercase rho underscore species, all lowercase. Let's do the same for species B. So for the molar mass, uppercase M and underscore, this time it will be uppercase B, and same here, lowercase, that is rho underscore species. Let's create another one by going to our reaction toolbar, species. Let's enter H2O here, and for our molar mass, let's enter our parameters. So that's it, M lowercase n underscore lowercase sol, and same for our density. If we go back to our parameters, you see here, so we have our density solvent, we have our density reacting species, we have our molar mass solvent, and of course molar mass A and B. So we entered those for species A, species B, and our H2O species. Okay, let's navigate over to our initial values. For our A values, for the concentration, let's enter that parameter, concentration in tank 1, and for the H2O, let's see underscore sol. Okay, now let's create our feed inlet. So we'll stay within the reaction engineering toolbar. Let's select feed inlet, For the volumetric feed rates, right here, let's enter V tanks, and for the concentration for the A value, let's enter C inlet, that's concentration inlet underscore A, and concentration all should be lowercase, the concentration solve. So let's close this. We're going to right click on this reaction engineering tank 1. We're going to copy it and right click on components 1 and let's paste it. And you will always have this once we copy the engineering reactions, the reaction engineering tanks. So let's click OK, and we're going to expand this reaction engineering tank 2 because we now need to adjust the settings for tank 2. Let's start with the initial values. So select initial values, and for the A value, let's change it from 1 to 2. Let's navigate down to the feed inlet, and for A, we're going to make some different changes. So for A, let's call a tank 1, and for the B value, so we're going to leave H2O as is, enter the B value. Now let's close reaction engineering tank 2. You're gonna right click, you're gonna copy, let's right click on components 1, paste reaction engineering, OK, and let's expand reaction engineering 3. Let's go to our initial values. One simple change, of course, it will be tank 3 for this one, and then we need to navigate down to our inlet feed, or feed inlet, and let's change the A. We're going to take out the 1, we're going to put 2 for the A and the B. Okay, let's navigate back to the initial value. Let's take a quick look. Yeah, that looks okay. Let's close reaction engineering 3 as well. Let's save our project. So I'm going to call mine that. You can call it anything you want. So let's save that, and let's go to our study, time dependent. Let's click on that. For our output times, let's change the middle value to 1, and our third value, let's change that to 600, and that's seconds. Now let's save again, and let's hit compute. Let's right click on our open loop, and let's add a global. Let's navigate to replace expression, and for the y-axis data, that is, so we click on expression, and component 1, reaction engineering, and we should have here tank 1, concentration A. Let's double click on that. Let's add another, so add expression, and we're going to the same component 1, but this time we go down to reaction engineering 2, and we're going to select tank 2 A concentration, double click that, and we're going to do the same for tank 3. So reaction engineering 3, tank 3 A concentration. Let's hit save. Let's navigate down to the x-axis data field, and for the parameter units, we're going to select minutes, and for the time, we leave that as time. Okay, so parameter, we have time, we're going to leave that for now. Units, minutes, let's add an expression. For the rather time, let's add expression, and let's put T, and let's go down to our legends, and we're going to change that to manual, and we're going to enter for our legend tank 1, enter, and then click inside here, tank 2, enter, click inside here, tank 3, okay, and let's hit plot. Let's look at this a bit closer, zoom to extents, make sure everything comes in nicely. So here we have the concentration transient for the 3 tanks in series, but this is without the feedback control. And as you can see, it takes approximately 600 seconds, which is approximately 10 minutes before the reactors reach a steady state. But I rather see this in minutes, so maybe we made a slight error, and that can easily be changed or corrected. So down to x-axis data, units changing from seconds to minutes, we plot again, and as you can see here, okay, so this is tank 3, so it started to get more steady, approximately from 6 minutes, and it reaches a complete steady state at 10, and the same for tank 2 and tank 1. Now it's time to set up the feedback control to model a closed loop system using the global ODEs and the partial differential equations interface and some other variables. So let's go home, and we're going to add a physics. So here, let's add a physics. Let's go down to mathematics, expand ODE and DAE interfaces. You can double click on it, but you can just click global ODEs and DAEs, and just add 2 components. Let's close this, and let's expand equation. Let's see the equation forms. Okay, leave as is. Let's go to global equation, and let's just bring this out a little bit, and we're going to enter our global equations. So let's go ahead and do that. Let's scroll down to units, and let's select define dependent variable unit. So we're able to enter what we want here. So we're going to enter mole per cubic meter multiplied by seconds, and for the source term quantity, let's select source term quantity right here, and let's enter concentration for the type. So concentration, and let's click filter. So we need another C here, filter, and let's double click on this, or you can just select it and click OK. Now let's create our definitions, variables. So this is different than the global definition parameters. So under components, there is definition. Right click on that, variables. Now let's import those variables. So I have a text file here, and also I have a CSV file, but I'll use a text file. And let's import those, and let's go to our home toolbar. Okay, we're already there, and let's click compute. Okay, so now we are going to plot the concentration of species A in all 3 tanks and at the inlet for the closed loop system. So now we're going to add our feedback loop. So in order to do this, let's right click on open loop. We're going to duplicate that. So with that selected, let's scroll up to the top, and let's call it closed loop, and we're going to change the data set to closed loop, from open loop to closed loop. And for the title, that's okay, and everything else should be okay. But let's just double check. Yeah, legend outside, okay. Alright, that looks good. Now let's expand closed loop and click on global 1. For the y-axis data, let's add an expression, and under component 1 we'll need to expand definitions. Let's expand variables, and where we have concentration inlet A, let's double click on that. Okay, and let's go down to our legends, and let's add another expression for that. So let's go back down here, and let's add inlet to tank 1. Okay, so everything looks nice there. Let's hit plot. Let's bring this a little bit bigger, zoom to extend, make sure everything is looking nice and neat. So as we can see here, This figure really demonstrates the fluctuating concentration levels within the closed loop system, because remember, our open loop system is without the control and our closed loop system is with the control. So this system regulates the final product concentration by adjusting the starting concentration of the initial process. And as you can see here, the set concentration is 100 mole per cubic meters, or 100 moles per cubic meters, and the feedback control appears to be reasonably tuned to keep the outlet concentration from tank 3 at our desired level. So this concludes this interesting study and simulation using COMSOL Multiphysics. Thank you and bye for now.